Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 34, WebSocket servers, coming from the previous episode where we spoke about PostgreSQL. So WebSocket servers, I already mentioned in our episode about HTTP servers, because there I made sure I will only show you the ones that have an HTTP upgrade to allow to swap from the HTTP protocol to WebSockets. And that's what I'm going to show you also in today's example, where we will use WebSockets to implement a small chat server that allows you to interactively chat with other people using the WebSockets protocol, and therefore we will use the libraries we did the last time, Fast API for Python and Warp for Rust. The Python example will be a bit easier than the Rust one, because in Rust we will have to manage way more the resources and message exchanges within the application. But anyways, let's jump into the code. On the left, as usual, we have our Python code. On the right is the Rust. For Python, I have written a small atomic counter library. All it does is lock an integer to increase it by 1. This way we can give every user that connects a unique ID, and we can store that in a dict, which you will see later. From Fast API, we are using the WebSocket class, of course the Fast API instance itself, and we are supposed to handle a WebSocket disconnect error. Our WebSocket server will run on top of a small HTTP server that serves the JavaScript-based client. And that's why it is very good when you can combine your web server with the WebSocket server within the same source code, because then all you have to do is power up this one daemon and you have both protocols implemented. Let's quickly go over the Python code. We start as usual by making an app instance for our Fast API. And here we have our connection manager class that I will get into a bit later, because first I will have to show you the other code, the other code, and then the connection manager will make more sense. In order to handle our WebSocket connections, we will have a global instance of our connection manager. But first we need to serve on the normal HTTP via get our JavaScript-based client. So directly as the index or slash of our web server, we will host this index HTML that holds our chat client. And that's why we read in this file and provide the HTML response with its content. The reason this file is actually in a parent directory of our Python project is it is also used for our Rust code. So you can see here that we are doing the same on the Rust side, because the client will be the same. It's talking the same protocol and the same implementation. Down here, we have our decorator that handles the WebSocket. The cool part is this does the HTTP upgrade magic for us, the whole setup and takedown of the WebSocket connection. WebSockets are different to HTTP in the way that HTTP is stateless. You would normally connect to the server, issue your request, the server would answer and close the connection right away. So if there was later information the server would want to send you, it cannot, because the connection was ended. WebSockets would be similar to TCP sockets, so you can interactively exchange information between server and client as long as the connection is established. We will use this interactivity to write our small and simple chat server, and let's go into how this works. So once you used the decorator for WebSockets, you will have to write an endpoint. So I called it creatively a WebSocket endpoint that gets past a WebSocket instance of our Fast API. And then we hand over this instance to our connection manager. And since all of this is asynchronous code, the methods of our instance are as well async. So here we await for the manager to finish connecting and setting up what it needs to do internally. I will get into this once we scroll back up to the code again. We set up our exception handling to react to a disconnect. So if a client disconnects, we can handle the disconnection by unregistering the user that came in and by running the necessary disconnect handshake for WebSockets. Plus, we let the other users on the chat know that this person has exited the chat. In order to handle the incoming connections, we start an infinite loop where we would receive text messages that come in from the WebSocket. This is very easy to do with asynchronous code because here we only advance if there is actually a text message coming in from the client. And once this happened, our manager will broadcast this message to everyone else that is connected to the chat. And you can see here in the formatting string, this will fetch the client ID using the WebSocket instance that we passed, and we will also use the WebSockets instance as a second argument so that we know inside the connection manager which is our own connection, so we don't broadcast to ourselves. We, the client, we know what we have typed. We don't need this to be sent to ourselves. Right, let's hop up to the block where we implement the connection manager. So when we create our instance, which happens here in line 32, what will happen is we will set up the atomic counter. So this will be 0 here, the user counter. And we have no active connections, so we have a dictionary that will keep track of all the connections to our chat server. Once a person connects to our WebSocket and has successfully upgraded, this is happening here. So the connect method will be called with the WebSocket instance. We accept a connection. If this worked out, we can now increment our atomic counter. We get our client ID. We use this client ID to add a new entry to our dict with the client ID and the WebSocket. On this connection, we figure out the client ID for this WebSocket, and then if we have found the client ID, we can remove it from the dict, and therefore we keep track of all active connections to our chat. The client ID is a very inefficient way of dealing with this, but in Python it's fairly easy. All I have to do is take the WebSocket value, try to find it within the dict. So I will get all active connections items, try to figure out if the WebSocket in there is our WebSocket. If it is, this will return the user ID. Implementation detail here, this is a generator. So here we have the parentheses for the generator that will generate the UIDs found. It should only be one UID, so I'm counting on the next iterator to give me that. If it fails, it would return none. Continuing to our broadcast method, we get past the message that we want to send out. You remember that we are formatting it in a way where we will use user ID, sed, and then the text. And we get past our WebSocket instance. In order to broadcast, we go over all connections in the active connections, but we are filtering by our own WebSocket so that we don't send to the client that just sent the message the broadcast message. As I said before, the person has typed the message themselves. They don't need to see it again. And then all we have to do is use the connection that we iterated over to all the other clients of the chat and send a text message with the message that was passed to our broadcast method. So this is fairly straightforward and easy to do because in Python we can use global variables. We can count on the fact that dict operations are more or less atomic because the global interpreter lock does this for us. Since this is asynchronous code, I still had to implement a locking counter with the atomic counter. Otherwise, there might be a race condition, and two people would, or two chat members would get the same chat ID. That concludes our server in Python. The Rust code is way more complicated. That's why I prepared a drawing, and I will now swap over to a split screen where we look at the Rust code plus the drawing, hopefully giving a better overview of what's happening there. The idea, however, you can quickly see is the same. So we are using a hash map as the storage for our users. As you can see here, we have the users type, which is a reference counted read-write lock hash map that holds the senders for messages, and the ID is an atomic usize, so also an atomic counter. We are also serving the JavaScript client, but the actual message passing is way more complicated. So let's jump over to the better view of explaining that one. All right, welcome back to my setup with the split screen. On the left, the Rust code, and here we have the overview of what's happening with the messages. Let's run over the code Let's run over the code a bit. As I already mentioned before, we are setting up a static user ID counter. We will have a static string that holds our HTML. So this is a fairly cool macro. This include string will actually include this index HTML file inside your binary. So once you copy the binary and hand it over to a friend of yours, you don't have to provide the HTML file. It will be inside your binary. Then here we have our smart pointer locked hash map. The MPSC, as you can see, is coming here from Tokyo Sync. So MPSC is for multi-producer single consumer. So these MPSC channels will have a sender and a receiver part, and the sender part we will put into our hash map. And the sender part also has to provide the data type it is sending around. So this can be either a message or an error. Hence, we are then wrapping this in a result type. The error, for example, can be the client has exited by, I don't know, a network problem. And this would be an error that needs to be handled. So we cannot just pass a sender only sending a message without handling errors. In our main code, you can see that we set up our users type with default values. So this will be an empty hash map behind the smart pointers. Once we have that, we can now make this a router. And this works in a way where every new connection to our Warp server will get a clone of this user's database. The clone here will be a clone of the atomic reference count and not a clone of the whole hash map. This is practical, as you can see down here. We will set up our new path for chat as we did in the Python version. Then we will hand this over to the Warp Websockets router. This handles for us the upgrade from HTTP to WebSockets. This then will be handed over the users router. So this is again is the one that produces the clones to the further steps in our routing chain. And then we map this to our WebSockets instance and to our users database. And when this WebSocket thing has an upgrade event, we call this closure, where we pass the socket in, and we call our user connected function that gets handed the information that we need, which is the WebSocket and our user database smart pointer. Here is the quick implementation for serving our chat client. This means that all we have to do is handle the warp path end right away. So / is the shortest path that can happen. This will then serve the HTML that we have statically compiled into the binary. And here we combine our routes. So we have our index route for serving the chat client, or we have our WebSocket chat. And that's literally how it's written in the code. That's very easy to understand for humans that have seen Forp the first time, which is pretty cool. All we have to do now is serve this route. And now we continue with the more complicated code that will be user connected. Okay, let's go over the user connected function. As I already said, it gets handed our WebSocket instance and the user's database smart pointer. First thing we do, because this is after the connection upgrade was successfully done, we can directly increment our user's ID to have a unique ID for this user that connects. We do this with the atomic useID fetch add method. Adding the number 1 and ordering relaxed is fine for our application. Then we would write this out to the terminal so we know that a person has connected if you are running or logging the server. This is a minimal solution for that. Next thing we do is we take this WebSocket and split it into the sender and the receiver, so TX for transmission and RX for receiving. Then we also set up our multi-producer single consumer channels, and as well this will return the split of sender and receiver. Next thing that will happen is Tokayo provides us the unbounded receiver stream. So we wrap our receiver of the unbounded channel into this receiver stream, because then we can spawn a task that will now forward every message that comes into this now wrapped MPSC receiver, forward it to the connecting WebSockets sender. So everything that gets received by this unbounded channel from its connected senders will be forwarded to the WebSockets sender, which then ends up actually talking to the client on the other end. Next step after this task that would forward our messages was spawned, we would write lock our hash map, wait for the lock to be acquired, insert the new user ID, and we insert the sender of our unbounded channel. This way we track all connected users, and we can in a loop then send to all of them a message if we wanted to, which will be handy later. What we do now is we make yet another clone of our user's smart pointer, because what we need to do is run a loop that uses the users here, and after this has been done, we need to use the user's database again to handle the disconnection of a user. What's happening in this while loop is for every message that's received in the WebSocket receiver, we handle it. So we try to figure out if this message is an error or a successful text message. And the same is also done up here in the forwarder. We map the results, and if the result is an error, we simply log out the error. But this also means that the spawn task has ended, because there is likely a networking problem that happened, or maybe the unbounded channel ran out of queue space. Handling the error also means printing out to standard error, and we break the loop, because this means that there is probably a disconnect happening or another networking error that will be not recoverable. And that's the cool part. When we break this loop, then we step out right away to the disconnected, where we will hand our disconnect of this user. So this way we don't have to handle any disconnect code in here. This will actually automatically be done at the end of this user connected function. So now we have established that our message is okay. That gets stored into here. Again, in error code, we would break out of the loop. So this user message function is the equivalent to the broadcast that we've seen in the connection manager of our Python code. We'll now use the user's database to send this message to every user that is connected. Looking at the diagram on the right, we can see the client A using his WebSocket client. When it connects, this will create for us the WebSocket receiver and the multi-producer single consumer sender. And then this sender gets stored into our hash map. Then this task A from our client A will be this while loop. So here we have our filtering. So this task A is this while loop, more or less. The loop filter we have not spoken about yet. This will be down here in the user message code. What will happen now is that this loop that reads every message that comes in from the WebSocket receiver will be sent via the TX that is stored in the hash map to the channel receiver, and we know what happens with the receiver. Once it receives a message, it sends it to the sender, which is denoted here. So once we have the WebSocket sender send it out, it will now actually, because we have done the loop filter here, go to our client B, so the other one in the chat room. And this one has a WebSocket client, just as client A does. And once this client sends out a message, it goes to our second client's receiver that has been set up here. So we run through the whole thing again. Now his second internal channel sender will be stored into the hash map. If the second client sent the message, it will now run on this new task that was created for this WebSocket connection. Will filter through, not sending back to itself, but to the other receiver, and indirectly using the sender that was found in the hash map with this loop. And then this goes to the client. And this is how we would exchange messages in our Rust server. When we now go down to the user message code, you can see that we need to actually filter for text messages. This is done in the easy form where we try to convert our message to a string. If this works out, then we store it in message. If it doesn't, we return directly from our function, ignoring it. WebSocket allows you to send ping, pong messages and binary messages as well. So not just text. Therefore, you have to make sure you're treating the messages that you are expecting. If you're setting up a protocol that exchanges binary messages, for example, which can be useful for games to keep the network bandwidth lower, then you would have to handle the binary messages, for example. Here we do the same thing as in Python. We format our messages in the format user ID, coming here. And then, of course, the message gets formatted right after. In order to send the message to every other user connected, what we do is we get a read lock on our hash map. Once we have it, we iterate over the user ID and the sender part of the channels. If the ID is not ourselves, we actually try to send the message. So we now use this MPSC sender to send a result of a WebSocket message of type text with this new message that we have created here. We need to clone it because within the loop, we will send off this message multiple times potentially. So we have to give up ownership. Here, as the comment already tells us, we have to not react to the error. And that's actually good, because if one user disconnected, we would break the loop if we handled it somehow or wrote a break here. We want to be sending this to all the other users as well. So we can ignore sending this. And you remember, if there is a failure within the forwarding stream, this will break the loop and end the WebSocket anyways. So there's no handling to be done out here. Quickly, the implementation of the disconnected user. So when our while loop was ended, all we are doing here is we pass the user ID in and we get a write lock on our database and remove this ID. And this way we keep track of the person that logged out. So this loop within the user message handling is this loop filter. I hope this kind of helped to get an overview of how this actually works. Now let's quickly run this thing. This means I will fire up the server and serve to the website, I guess. This means we do a cargo run. All right, we are back with our demo clients. What I did is I created 2 iframes that load the index website. So they load the demo chat. And you can see here already we have 2 users connected. If I now type something in the first one, it will be hello. And then I can welcome to bedroom builds. And you can see that the chat client knows what they typed themselves. They receive the message of the respective other chat client with the user ID attached. And if we now close the window, you can see that we get the goodbye user messages of the chats disconnecting. Thanks for watching. Coming up next at the From Python to Rust series will be writing a WebSocket client in Python and Rust.